Hello everyone. So I'm going to talk a bit about low depth tree augmentations. What is a tree augmentation? So the idea is we start off with a network which is a tree in the sense that the removal of any of the connections in the network will disconnect the network. So it's minimally connected. So the failure of any single edge immediately disconnects the network. So two nodes can't communicate. And we're trying to make our network more robust to these failures. So there might be some other edges that I can potentially add into my network and make it more connected. So here I've drawn a bunch of dashed lines, and these represent what we call the links. These are edges that I can potentially add in. And note that if I add in this subset of links, then actually the graph becomes two-edge connected. Two-edge connected meaning that the removal of any single edge will not disconnect the network. So that's the tree augmentation problem. Like formally, we're given an undirected tree and a bunch of links, and each link has an associated cost. We want to pick the cheapest subset of links to add to our network so that the resulting network is two-edge connected. So the tree augmentation problem can actually be viewed as a covering problem. Recall that a graph is two-edge connected if and only if every edge is contained in a cycle. So like this edge, if I remove it, the graph has to still be connected. That means there's another path. So that path and the original edge forms a cycle. So every edge is in a cycle. And the addition of each link into the network induces a cycle because there's a unique path between the endpoints of the link in the tree. So the tree augmentation problem can be viewed as picking a subset of links whose cycles cover all the edges of the tree, and then pick such a set of minimum cost. So, that's kind of the problem. And, if we view it in that light, we can write down a set covering linear relaxation for the tree augmentation problem. So here, I've written a linear program. It just has one constraint for every edge saying that it must be covered by the links we've selected. And then we're trying to minimize the cost of our subset. So this is a valid linear relaxation, but it is not a perfect formulation. I've drawn a small example here. In this graph, you need to pick at least two links in order to make this network two-edge connected. But if we're allowed fractional entries, then putting 1/2 on each of the links is a feasible solution to the linear program. So, this gives an integrality gap of at least 4/3 for this relaxation. And it's actually, in fact, worse than that. Cherion gave a series of examples showing that the integrality gap is at least 3/2. But to summarize, the state of knowledge about the edge LP, the set covering relaxation, is that the integrality gap is between 2 and 3/2. And, since it's at most 2, this immediately gives a 2 approximation for the tree augmentation problem because we can solve the linear relaxation efficiently. But it was actually open for a very long time to get a below 2 approximation for the tree augmentation problem. And very recently, a new result came out. Traub and Klusen showed that you can get a 1 plus ln of 2, which is less than 2, approximation for the weighted tree augmentation problem. However, they do not shed any new light on integrality gaps of the associated linear relaxations, and so that's what we were interested in. So we work with not the edge LP, but a stronger LP called the odd LP, and that's obtained from the edge LP by adding in the 0, 1/2 Kvatal cuts. So when we do that, we obtain a new set of inequalities. Like we still have the old ones, but we also have an inequality for every odd subset of edges in the tree now. Which, you might be thinking, that's an exponential number of constraints. How is that helpful? But it was shown that we can actually separate the odd LP in polynomial time. So we can actually optimize over the odd LP efficiently, even though there's exponentially many constraints. So the punchline here is we show that the integrality gap for a depth k instance of the tree augmentation problem is at most 2 minus 1/2 to the k minus 1. And this is always going to be below 2, but it approaches 2 as k grows large, so it doesn't actually provide a better than 2 approximation in general. But if we are looking at a small depth instance, like if we have a depth 2 instance, this gives us a 3/2 approximation, and in general, it doesn't give us a bounded away from 2 approximation because k growing large has the gap approaching 2. But yeah, that is our result. I just wanted to give an introduction. Thank you.